A warm welcome to ISRM lecture series on deep mining. Good morning, everyone. Good afternoon or good evening. With the evolution of mineral industries and the complex lifestyle of growing world population, the resource industry, including minerals such as rare earth minerals and hydrocarbon recoveries, large-scale hydrogen storage, renewable energies from deep earth, large-scale CO2 mitigations, including geological storage of carbon dioxide, needs development of new technologies to recover or store them in sustainable manner, both environmentally and economically. To discover and develop new extracts and groundbreaking know-hows, we need to have state-of-the-art testing, apparatus, unique equipments and tools. Today, I want to talk about some very interesting research and development of unique testing rigs we have designed and developed in-house. In my other ISRM video lecture, I introduce a new in situ rock breaking technology called as REMA, slow releasing material agent, which I believe it will transform the mining industry to sustainable industry with less energy in footprint. Let me first give a brief introduction to myself. I'm Ranjith Pathegama, a professor in sustainable development of technologies for resource recoveries at Australia's Monash University. I'm a fellow of the Australian Academy of Technology and Engineering and editor-in-chief of Geomechanics and Geophysics of Geoenergy and Georesources, a Nature Springer journal. The journal is one of the flagship journals in energy and resource areas. I'm the founder and a director of Geomechanics for Geoenergy and Georesources, commonly known as 3D Deep Earth Laboratory. For more than 2 decades, as civil engineer research and practitioner, I have dedicated my academic career to pursuing two goals that are typically portrayed as diametrically opposed: protecting the environment and extracting resources, both energy and minerals, from the earth. As more and more humanity are coming to realize neither of these goals is negotiable, we cannot continue to damage the environment at the increasingly unsustainable rates we have been for the past century or more. Climate change, species extinction, water shortage, and countless other problems are forcing us to take environmental sustainability seriously. Yet we equally cannot just give up on recovering resources from underground, given their importance to human well-being. How can these mineral and energy vital sectors be made less energy intensive and more environmentally and economically sustainable? This question is the driving force behind my career in geoengineering. The broad unifying theme behind my contributions is making better use of Earth's energy and resources, while simultaneously reducing their impact on the environment. For example, in addition to new rock breaking technology, I developed a carbon neutral, environmental friendly cement that uses up waste products from the energy and steel industries. I also use similar waste products to create high-yield, environmental-friendly fertilizer for the agricultural sector. With that small introduction, now let me to go into the main lecture outline. This lecture is structured as follows. Before moving to the main topic, I thought to provide you a brief overview of the necessity of experimental infrastructure for deep mining research and the multi-scale approach we adopt in the 3D Deep laboratory to give you a bit of context. There are many experimental facilities that we have developed over the years in the 3D Deep Research Laboratory at Monash University. Today I am going to introduce 7 of those unique facilities in this presentation. I hope these will provide valuable insights for your advanced experimental research. While conventional mining has a strong negative perception at the moment, one thing we cannot forget is that we are heavily relying on resources and energy extracted from the earth. I firmly believe climate change is one of the biggest challenges facing the world, and the world must and is transition to low carbon economy. The correct use of the subsurface has great potential to aid the transition to low carbon energy. At the 3D Deep Research Group at Monash University, Australia, we are exploring critical aspects of resource recovery, promoting technological innovations for environmental protection and safe and practical resource recovery from the deep earth. We are working on a number of themes related to deep mining, including mineral extraction, deep geothermal energy, geological storage of carbon dioxide and hydrogen, coal seam and shale gas, and gas hydrate extractions. We have developed unique experimental facilities in our 3D Deep Research Laboratory, which enabled us to conduct advanced experimental research across these different themes. First of all, why do we need experimental facilities for deep mining research? Deep mining will be inevitable in the future due to the energy and mineral resources at shallow depths gradually become exhausted. At present, deep mining at 1000 meters is normal. Depth of coal mines has reached to 1500 meters. Depth of geothermal exploitations has reached more than 5000 meters. Depth of non-ferrous metals mines have reached around 4500 meters. And the depth of oil and gas exploitations has reached around 7500 meters. Underground mining continues to progress to greater depth to sustain the supply for the growing demand. This means we require to characterize deep rock mass which is subjected to high in situ stresses, high temperatures, and high fluid pressures, since existing fundamental theories might no longer be valid. Considering this necessity, over the last 2 decades, tremendous development has occurred in experimental laboratory facilities around the world. Here at Monash University, Australia, we have developed state-of-the-art research facilities to conduct advanced deep mining research. Our 3D Deep Research Laboratory employs comprehensive 4-stage modeling regimes to capture the whole process from the micro scale to the reservoir scale, as you can see in this image. There is a capability at 4 scaling phases. Micro scale 3 micron to 20 millimeter, meso scale 20 to 100 millimeter, macro scale 100 to 1000 millimeter, and reservoir scale over 1000 meters. This approach enables us to understand micro-scale observation, for example, available for areas, rock fragmentations, tortuosity in fluid flow through pore structures, and leaching, and apply fundamental physics in reservoir scale. Studying the relations among these 4 scales assists in capturing the essential geological characteristics needed for a comprehensive reservoir scale model in the real field conditions. This slide provides a quick overview of how we have conducted experiments over cross scales and integrated these approaches to understand the field scale reservoir conditions. Our unique large-scale triaxial stress reactor, large-scale triaxial testing rig, advanced core flooding and shearing devices represent the macro-scale facilities. Meso-scale equipment at 3G Deep Laboratory includes custom-made high-pressure, high-temperature advanced rigs. Micro-scale equipment includes an X-ray microscopy facility for 3D contrast imaging, computerized tomography CT scanning, scanning electron microscopy SEM, and XRD. Among these numerous facilities that we have developed, today I am going to share the most exciting ones in my view, which will provide you with good understanding of advanced experimental research that can be related to geomechanics and other engineering applications. First, I would like to present one of our unique super deep stress reactor for mineral and energy recoveries. To the best of my knowledge, this is the world's largest triaxial stress reactor capable of testing cubic specimens up to 750 mm in length. In the next few slides, I will take you through the highlights, operational procedures, and potential applications of the setup. This super deep stress reactor for mineral and energy recoveries is in a class in itself, measuring over 3.5 meter wide and 5 meter in height. It weighs over 60 tons. The setup was designed and developed at Monash University over a number of years. One of the local companies in Australia fabricated it. The stress reactor is capable of exerting a compressive stresses of over 270 MPa for the smallest specimen size and can simulate high temperature conditions of up to 400 degrees C. The setup is also capable of true triaxial and isotropic loadings. The high rigidity of the stress reactors allows post-failure stress measurement of specimen being tested. Now let us have a look at the internal details of the setup, which makes laboratory simulation of these extreme geological conditions possible. First is the bulk of the setup, which is the reaction chamber. As shown in the figure, the setup consists of 3 hydraulic loading ramps in 3 reaction plates. The large forces exerted are measured in each reaction plate by 5 high-capacity load cells, 25,000 kN in total in each axis. As you can see, the reaction chamber itself is quite large, and we can change the setup loadings or reaction plates to accommodate 3 sample sizes, 350, 500 and 750 millimeters. We can go for even smaller sizes to accommodate very large stress over 400 MPa. As of currently, the smallest we can comprise is 350 millimeter sample subjected to 250 MPa pressures, and the largest specimen can be confined up to 45 MPa. On the right, you can see the spacer setup for smaller specimens that can be mounted for the loading pattern. The next major component of this setup is the hydraulic loading system. The hydraulic circuit consists of a quad pump, one of each loading ram and one for hydraulic oil recirculations. The load on the specimen is controlled by solenoid actuators. A schematic of the hydraulic circuit is shown to the right. The high power heating system is another unique component of this setup. We have connected each loading reaction plates to two heating elements, and the temperature is controlled with thermocouple connected to each platen. The figure on the right shows the heating element and the thermocouple connections of the top loading platen. The heating elements in the setup are capable of increasing the temperature in the reaction chamber to 400 degrees C. Now let's move to the brains of the stress reactor, which is the integrated control unit. The loading and heating system is controlled using bespoke control software. The control unit allows independent control of the loading ramps to adjust specimen positions within the reaction chamber. As you can see in the figure to the right, the user can apply true triaxial or isotropic loading to a specimen. We can also select loading rates in each axis, heating and the specimen size in the setup. Now, having an idea of the different components of the stress reactor, let's look at the specimen preparations and loading procedures. For commissioning the setup, we have produced a large 750 mm cubic mold and casted concrete blocks for testing. These blocks are placed in the reaction chamber using 12-ton Granite crane sitting above the test setup. We move the blocks by drilling anchor bolts into the specimen to allow hosting. As indicated in the bottom left figure, the reaction plates positions are fixed and the block is placed in contact with the three reaction plates. Then the top cap is placed and locked in position using the steel dowels. We manually adjust the position of the reaction plates before setting the specimen. Upon completion of the setup, we conducted an initial experiment at our 3G Deep Lab at Monash University. The tested specimen was a grade 35 750 mm concrete block, and both temperature and load applications were done simultaneously. We heated the specimen up to temperature of 250 degrees C and applied initial biaxial stress of 35 MPa in the horizontal directions, followed by additional vertical stress of 35 MPa. Here you can see the temperatures of the heating elements on the left and the stresses applied on the right. In this figure, C1 and C2 corresponds to the X and Y directions, and C6 is the vertical direction. In this slide, you can see the control system and fluid injection pump system for the true triaxial setup. There are three fluid pumps that can inject, for example, carbon dioxide, nitrogen, water at high pressures and high temperatures. The control system displays the fluid pressures and allows the control of fluid injections into the specimen. And it is also possible to obtain acoustic emissions data from the system using the acoustic emissions monitors. So, having developed a mammoth super deep stress reactor, what applications do we have for the setup? First, the large scale of the setup allows us to simulate high temperature and high pressure in situ stress conditions in the macro scale. This ability gives us the unique opportunity to simulate various complex geological conditions in the laboratory environments, including stress-strain responses of anisotropic of geomaterials, including shale formations for oil and gas extractions, evaluation of well integrity for oil, gas, and in situ mineral recoveries, deep earth simulation of host rock preconditioning using different technologies such as non-explosive demolition agents that we have developed, and we call them as SREMA, slow releasing material agent. In situ leaching, simulation of hot dry rocks for enhanced geothermal system, rare earth minerals extraction and fault simulation, spatial distribution and proper embedment under high in situ stress conditions, and hydrofracturing. The control test we can perform using this stress reactor allow us to closely monitor the mechanical response of rock matrix in deep geological conditions on large scale, which we were previously not possible. We are currently experimenting with large-scale rock fragmentation technologies with this setup with our newly developed fracturing compound, particularly simulating fracturing with multiple boreholes. Next, I am moving to another very unique laboratory facility, our large core flooding apparatus that we are extensively utilizing for a number of applications. This advanced facility can be used in a number of applications to investigate and develop technologies related to carbon dioxide sequestration in deep geological formations, in situ leaching for recovery of metals, shale gas and coal seam gas explorations, geological storage of hydrogen, wellbore stability and extraction of hydrocarbons. We widely use this facility to monitor the flow, diffusion and permeability characteristics associated with the different types of fluids and the mechanical responses of the reservoir in the applications listed here. Next, let's have a look at the key features of the advanced large core flooding apparatus. This apparatus consists of four main elements: high pressure cell, hydraulic loading system, fluid injection system, high precision measuring and data logging system. The maximum working temperature of the facility is currently at 100 degrees C, and the cell is covered with a thermal blanket to achieve the operating temperature. This temperature can be modified to even higher temperatures of up to 200 degrees C. We have installed 4 pressure transducers along the cell at 350, 600, 850 millimeters and at the downstream end to observe the pressure development profile along the sample. Those pressure transducers are connected to capillary tubes to facilitate the installation and removal. We have placed a custom designed porous sealing bunk between the sample and injection line to hold the sample and ensure an evenly distributed fluid flow. The hydraulic loading system can provide up to 100-ton axial load through the loading ramp, on which a linear variable differential transducer (LVDT) is attached to measure the movement of the loading ramp. We can use the reading from the strain gauges to calculate the sample volume variations during the test. We have used 3-phase motor and pneumatic pump to provide a proper load to the sample in the loading system. The high pressure fluid injection system is controlled by a Teledyne ISCO 260D syringe pressure pump with a maximum pressure supply of 50 MPa. And the fluid plumbing lines are all compatible with different types of fluids, including carbon dioxide. We have designed this high pressure cell with a bore diameter of 203 mm to accommodate sample with length of 1000 mm. This means we can have a maximum sample diameter of 203 mm and maximum length of sample is 1000 mm. We can vary the sample sizes within these ranges. The rig is capable of taking natural and reconstituted samples. The figure shows a reconstituted core sample. The actual stress for the largest sample is 30 MPa and the horizontal stress is 40 MPa. And the fluid injection system can go up to 50 MPa. The system is capable of injection of 3 fluids, for an example, water, gas, and oil, to simulate multi-phase flow conditions encountered in number of subsurface applications. We have conducted many research studies using the advanced core flooding apparatus, and I'm going to briefly talk about some of them to give you an overview of the capabilities of this facility. One such example is use of CO2 to recover methane and the associated CO2 storage in core seams. CO2 becomes a supercritical fluid at 31 C and 7.4 MPa pressures. Its physiochemical behavior is very different from gas. When we inject CO2 gas into coal, flow through the coal matrix creates significant differences when CO2 reaches its supercritical state under reservoir conditions. Therefore, we need to understand CO2 flow patterns along the coal for different injection pressures and different temperatures, considering CO2 phase transitions. We can easily achieve this using this large coal flooding apparatus with the intermediate pressure transducers along the sample length. We have used our experimental findings to develop relationships to study how this CO2 flow varies through the coal sample length during each injection conditions under different in situ stress scenarios. This enables us to predict the potential pressure development profiles in the feed. The slide shows development of some empirical equations and some modeling works we have carried out, and these have been validated with experimental data coming from this test rig. Further details can be found from the paper published and shown here. Only a few studies to date have investigated CO2 sequestration using large-scale core samples. We have conducted several detailed experimental studies to identify sub- and supercritical CO2 flow behaviors in coal using large-scale reconstituted both low and high-rank coal specimens. The specific coal we used for this research is sourced from Victoria, Australia. It can be seen from plots how permeability varies during the transition from sub to supercritical CO2. The developed permeability equation is function of stresses and fluid injection pressures, and the heterogeneity is negligible because of reconstituted samples. We used a quantitative approach to identify the real swelling effect created by CO2 absorption under different injection conditions by measuring the sample volume change under each injection condition. The third and fourth plots show huge swelling observed with CO2 and in particular during the supercritical phase of CO2, that is beyond 7 MPa pressures. One of the main purposes of CO2 ECBM enhanced coal bed methane process is to store anthropogenic CO2 in deep unminable coal seams and to recover methane. Therefore, it is very important to investigate the amount of CO2 that can be stored in the coal mass under various reservoir conditions, including various seam depths and injecting fluid properties, for example CO2 phase and pressure. We used our core flooding setup to quantify the CO2 storage capacity in the coal mass under the various test conditions. We could accurately monitor this using a digital platform scale at the CO2 injection point. Further details of storage capacities could be found from the paper published shown here in Geomechanics and Geophysics for Geoenergy and Georesources Journal. Geothermal energy is considered as true form of renewable energy. Number of studies have shown that we have huge amount of energy being trapped underneath. For example, just over 1% of deep geothermal energy in Australia could provide all of Australian electricity for the next thousands of years. However, we have huge challenges, including stimulation of the hot dry rock body for the increased circulation fluid. This is where our group is advancing to develop new rock breaking technology. Deep geothermal research work is another area that requires advanced experimental facilities to simulate reservoirs at 3 to 5 kilometer depths under extreme temperature and pressure conditions. We have developed unique solutions and new technologies to fracture the rock and enhance fluid flow and heat extractions. Here is our unique deep geothermal testing facility that can simulate a geothermal environment over 5 kilometer depths. We extensively utilize this testing rig to understand the thermomechanical behavior of rocks, reservoir stimulation using water and supercritical CO2, as well as flow behavior of fractured rocks at high pressures and high temperatures. This system consists of several main components: the pressure vessel, the loading system, the confining system, the fluid injection system, and the heating system. We have used 3 high-precision syringe pumps in this apparatus for fluid injection, applying confinement, and axial loading, as you can see here. The directional pump allows us for coarser movement of the piston of the hydraulic cylinder. The heating unit comprises a mica insulated metal band heater that is used to heat the pressure cell and consequently the rock sample. Currently, we are developing new circulation fluid as well as new stimulation fluid to replace water-based fracking, which is not environmental friendly and has bad public perception. Here you can see how this system looks like once deassembled. Some of the unique and innovative features of this cell are the extensive range of operational conditions. We have confining pressures over 150 MPa, temperatures of up to 350 degrees C. We can inject both water and CO2 over 165 MPa. The loading system has been designed to withstand up to 100 tons of axial load. We can make direct measurements of temperature, pressure, displacement, and fluid flow rates using various sensors and thermocouples. Here is the inside view of this system. You can see how the fluid injection lines are connected to the top plate. We use 2 types of bottom pedestals for permeability and hydraulic fracturing experiments separately. We used a bottom pedestal with the top O-rings for the hydraulic fracturing experiments. Permeability experiments were conducted with another bottom pedestal with machine distribution rings on the top surface to ensure the uniform distribution of the injection fluid into the sample. You can also see the specimen covered with an annealed copper sleeve. We are talking about above 200 degrees C and extreme confinement and injection pressures. So we cannot use available latex or Teflon membranes. Our innovative solution is a custom-made copper sleeve. We annealed it with an oxyacetylene flame and water quench it to make it extremely soft and ductile. Now, I would like to briefly go through a couple of the research studies that we have conducted. We know traditionally rock failure in compression can occur in two main ways: dilatancy and failure by strain softening under relatively low confining pressures, and failure by strain hardening under elevated confining pressures. Also, the mechanical behavior of reservoir rock is significantly influenced by elevated temperatures due to the thermally induced microstructural alterations. This is experimental evidence of how the rock failure will alter with extreme confining pressures and temperatures with a transitional regime at intermediate pressures. Further details of the findings can be found in our paper published in Geothermics journal. Our deep geothermal testing facility enabled us to conduct a comprehensive laboratory scale hydraulic fracturing experiment series under extreme temperature and pressure conditions for the first time, and it is published in Fuel Journal. Here you can see a typical pressure time curve during hydraulic fracturing, often known as breakdown curve. We found that breakdown pressure linearly decreased with increasing temperature, while the rate of reduction decreased with increase in pressure. We could correlate the thermally induced damage and the linear reduction of breakdown pressure with the temperature-dependent tensile strength of granite. Supercritical CO2 fracturing of granite rock is another interesting research that we have conducted. Though we have conducted many experiments for supercritical CO2 fracturing at moderate temperatures around 60 degrees C, but this is the first time we have done this supercritical CO2 stimulation at high temperatures over 200 degrees C. You may refer the paper published in Journal of CO2 Utilization for any further information. We found that the breakdown pressure with the supercritical CO2 fracturing was 10 to 15% lower compared to water for the same conditions. CO2 fracturing also resulted in narrow fractures with multiple secondary branches under high temperature conditions. This is because of the low viscosity of supercritical CO2 fracturing compared to water, which has the ability to percolate into the weaker regions of rock with microcracks compared to water. One of our main objectives is to develop new fluid types for stimulation or fracking of the reservoir rocks to replace water-based fracking, which is being banned or under moratorium at many places around the world. With this in mind, I am going to introduce a unique laboratory-scale hydraulic fracturing apparatus that we specifically designed for fracking using foam-based fluids. We mainly use this facility for shale reservoir stimulation applications. We know that one of the unconventional reservoirs is shale gas, which has attracted more and more attention worldwide, specifically after the successful shale gas revolution in the United States. However, as a typical tight reservoir with ultra-low permeability and ultra-low porosity, the commercial development of shale reservoirs needs a series of artificial assistance such as horizontal drilling and hydraulic fracturing technologies. Compared to conventional water-based fracking, foam fracking has superior characteristics. Foam is a typical two-phase fluid that is mixed gas and liquid with some surfactants. And the volume fraction of gas inside the foam is foam quality. The gas content in foam can vary from 60 to 90% or even higher. Considering its subsurface applications, foam greatly reduces the amount of water consumption. Also, the viscosity of foam is much higher, ensuring a better proton carrying capacity as shown in the left picture. Here you can see the different components of this experimental facility. It has several main features. Foam generation component consists of gas-liquid injection lines and mixing device. Viewing cell, which enables visualization of generated foam. Capillary tube part for viscosity measurement. And triaxial system that enables to apply confining pressures of up to 70 MPa, axial load up to 250 kN. We can inject water, gas, foam up to 50 MPa injection pressures in the system under temperature up to 100 degrees C. Some research findings using this unique rig has been published in Engineering Fracture Mechanics Journal. Next, let's briefly look at a few applications of this newly developed fracturing test setup. Here you can see the foam stability test results of foam generated with 0.5% alpha olefin sulfonate surfactant. We have generated foams with 50%, 60%, 70%, 80%, and 90% foam quality. As expected, we observe that half-lifetime increases with foam quality. Further details of the apparatus and the detailed results can be found from the PhD thesis done by Dr. Ayal Waniarachi given in the slide. Here you can see selected test results of 75% quality nitrogen-based foam with 0.5% alpha olefin sulfonate surfactant, published in Engineering Fracture Mechanics Journal. We found that compared with water, the breakdown pressure of foam is about 30% higher. This is because energy release in foam is 11 times higher compared to water under these test conditions. This higher energy release is favorable for microfracture development. Due to the high compressibility, foams take a longer time to achieve the breakdown pressure compared to water. However, water consumption is 3 times lower in foams compared to water fracturing. Next, we critically evaluate the generated fracture characteristics using micro-CT scanning. As shown in these slides, we found that both fluids can induce radial fractures. For water fractured sample, the fracture is only part of the specimen. But for foam, the fracture is throughout the specimen. We also found that foam-based fracturing contributes a complex twisted fracture with greater surface area. The next experimental facility that I am going to share today is the large-scale constant normal stiffness shearing testing facility. This can be used for a number of applications, including deep file foundation, rock slope stability, fault simulation triggered by earthquakes, and proppant crushing and embedment in hydrofracking. We have extensively utilized this testing rig to investigate the influence of proppant crushing, embedments, and displacement behavior under various fluids and rock joint surface roughness conditions. The equipment has the capability to apply the normal load up to 225 kilonewton, and we can apply maximum shear load up to 225 kilonewton as well. And the maximum normal displacement is 84 millimeter, and the maximum shear displacement is 125 millimeter. And in this setup, we can very large samples of up to 600 millimeter long, 200 millimeter wide, and 75 millimeter deep. Here you can see number of applications that we have used this testing rig. Next, I am going to share with you some of research findings of propons embedments during shearing of rock joints, published in Journal of Petroleum Science and Engineering. The unique shear rig was controlled using the Advanced Shear Machine Control Platform. It has separate horizontal and vertical control panels to control the movement of each shear box and can record the data simultaneously. We used sandstone specimen with a size of 200 millimeter by 75 millimeter by 100 millimeter into the shear box. We used samples with a different joint roughness and propellant with a different coverages. Here you can see experimental works of two rocks of joint roughness coefficients of 0 to 2 representing smooth joint and 10 to 12 representing a relatively rough joint, and 1630 size ceramic propellant with 100% uniform coverage that were placed between the rock joints. We applied constant normal load in a monotonic way for this particular experimental work. We require to cast the plaster to fix the sample within the shear box. This is because the sample is not the same as the shear box size. Then we set up transducers at each side of the box before commencing the testing. The top right corner shows the experimental parameters used for this test. Moving on to the experimental results, we found that propan embedment increases with increasing normal stress, and the embedment rate sharply increases when shearing and horizontal displacement commences. For an example, embedment increasing rate after shearing is 10 times larger for smooth rock joint, JRC of 0 to 2, and 15 times larger for rough joint, JRC of 10 to 12, than no shearing conditions due to the rock dilation mechanism. In addition, the propan embedment increases nearly linearly within increasing horizontal displacement, as shown in the middle figure. In addition to the joint roughnesses, we looked at the effect of the introduction of propellant and fluid on the jointed rock. We found that the introduction of propellant has weakened the dilation pattern, especially under dry and water conditions, with a minimal effect under oil conditions. These findings have been published in our paper in the International Journal of Rock Mechanics and Mining Sciences. The friction angle is also one of the key parameters of shear strength development. We investigated peak, residual, and basic friction angles. We found significant peak and residual friction angle reduction with addition of propellants. There is a further reduction on friction angle with the addition of fluids. Overall, results show that there is a strong negative linear correlation between shear strength and introduction of propellants. The weakest correlation appears for rock when increasing the surface roughnesses, as the non-synchronism dilation leads to fluctuation of shear strength variation. Finally, the linear correlation between shear strength and fluid is more obvious for smooth rock joints with introduction of propellants. Moving on to the next interesting experimental facility that we have in our laboratory, in situ CT imaging of rock using novel X-ray flow cell. This piece of equipment allowed us to use X-ray CT to visualize microstructure of rocks at micron resolution at reservoir conditions of temperatures and pressures. Using this micro CT, we can image soil and rocks down to sub-micron resolution under in situ conditions with unconfined, one-dimensional and triaxial loadings. Some of the key features of the CT are given top right side, including high resolutions of 0.7 microns. Here you can see the details of X-ray high pressure triaxial flow cell. The body of the triaxial cell is composed of aluminium and compatible with X-ray CT scanning. This cell allows pro-scale imaging of fluid flow in porous rocks using X-ray microtomography combined with co-flooding experiments. We can apply axial and confining stresses separately up to 20 MPa and inject water or gas into rocks for co-flooding experiments. We can also wrap a heating jacket on the cell and heat up rock samples up to 200 degrees C. We can adapt the pressure transient method to measure the permeability of tight rocks to shorten the testing period. To image and look inside of rocks, we can either use the micro CT scanner or Australian synchrotron. The Australian synchrotron is conveniently located next to Monash Clayton campus. Compared to laboratory-based micro CT, the use of much brighter synchrotron source enables to achieve of high-quality scans in much shorter time. For example, we can scan a test that takes hours from conventional micro CT within minutes using synchrotron, which is much suitable for observing dynamic processes. Micro CT is an important technique to understand the fundamental mechanism of many engineering applications. Most of the research work in my group is related to understanding carbon sequestration and developing new methods to overcome resource recovery challenges in mining and specifically for unconventional gas and geothermal reserves. We have extensively utilized our micro CT lab for pore-scale imaging and analysis of the dynamic process of rock mechanics, CO2, hydrogen storage, conventional, unconventional oil and gas production, and many more. I will now present some recent experimental results on CO2 sequestration in coal. It is important to understand the complex physiochemical interactions between coal and CO2 to achieve the purpose of long-term storage. Upon CO2 injection into target core seams, typically about 800 meters in depth, CO2 exits in the supercritical phase. As I discussed earlier, supercritical CO2 interacts with both the organic and inorganic composition in coal and change in different ways. For example, coal matrix swelling upon CO2 injection and the associated permeability reduction and dissolution of CO2 into the formation, which in turn causes the dissolution of minerals such as carbonates and silicates, significantly influence the long-term sequestration. Our research on direct visualization of the 3D microstructural evolution of coal due to CO2 injection under reservoir conditions was critical to understand these mechanisms. Coal porosity and permeability are highly stress sensitive. However, the direct observation of the dependency of fracture aperture, porosity and connectivity on effective stress are minimal to explain this mechanism. We conducted X-ray tomography under stress conditions and characterized the coal fracture network evolution due to the increased stresses. This is a 3D fracture network change with increased stress conditions. We can directly see the large fractures were quickly compressed and isolated to small fractures in response to increased stresses. The porosity significantly decreased with the increase of stresses and followed a power relation. The experimentally measured permeability of the sample also exponentially decreased, showing the correlation between the permeability and porosity. The details of the works can be found in our paper published in the International Journal of Coal Geology. For many years, people realized water absorption on coal plays a significant role in coal permeability, but did not have direct evidence on how coal absorbs water and swells, affecting the permeability. Here we directly demonstrated that the swelling caused by water absorption induced fracture closure. We found that the permeability reduction was time dependent, as shown in the plot on the right side of the slide. There is a residual permeability in the final stage because the fracture apertures reaches a residual state. These are mineral supported fractures which have shown resistant to swelling induced stresses. If you are interested in further details, you may refer to our paper published in Geophysical Research Letters. As I discussed earlier, one of the main technical barriers for CO2 sequestration in coal is that CO2 absorption induced swelling reduces coal permeability and hence CO2 injectivity. Some field and lab experiments demonstrated that injecting pure nitrogen over a period can reverse some reduced permeability. In order to understand the cleat scale mechanisms, we conducted a series of co-flooding tests to indicate the permeability variation caused by injecting nitrogen, then carbon dioxide, and then again nitrogen, as you can see here in the experimental results. At the same time, we observed the cleat network changes in CT images at different injection stages. After nitrogen injection, cleats opened from their initial confined condition. This is because the decrease of effective stress after gas injection tended to mechanically open the cleats. However, the cleats narrowed down and even closed after injecting carbon dioxide due to the coal matrix swelling accompanying CO2 absorption. After re-injecting nitrogen, the cleats open up again and the cleat porosity rebounded to 50% of the initial conditions. We also conducted pore networking modeling to quantify the pore geometry. We found some large pores here in red color are mainly contribute to the connectivity and control the permeability changes for the fracture network. Pore scale imaging and modeling techniques help us to understand the underground flow processes and design effective gas storage and resource recovery. Here is the final experimental facility that I would like to share with you today. Among all the facilities that I discussed earlier, perhaps this might be the most utilized apparatus in my research group. High temperature, high pressure reaction chambers is an advanced experimental facility that can simulate deep underground conditions for long term. Some of the unique and innovative features of this setup are extensive range of operational conditions. We have confining pressures up to 12 MPa, temperatures of up to 100 degrees C for very long time reaction. For an example, for few hours to few years. We can use different gases for injection, for example, carbon dioxide, nitrogen, methane, or to use other type of liquid having both high pH and low pH, including lixiviants used in situ mineral leaching. The stirring motor and the rotating shaft help us to enhance the reaction rate by mixing the sample with the pressurized gas or liquid. We can make direct measurements of temperature, pressures using thermocouples and pressure transducers. Also, samples are taken in time intervals for chemical, mechanical, and image analysis. This experimental facility is versatile. When there is a necessity for long-term saturation or reaction under high pressure and high temperature conditions, my group often utilize this facility. So far, we have utilized this facility for different research themes such as carbon sequestration, soil carbon sequestration, saline aquifer simulation, mineral reactions, in situ leaching, as well as rock fluid interactions under deep geological conditions. We often couple with this facility with the other advanced analytical techniques such as electron microscopy, X-ray diffraction, CT scanning, chemical analysis techniques such as inductive coupled plasma spectroscopy technologies depending on the application. Next, I would like to briefly go through some of the research studies that we have conducted. We can store the carbon dioxide into fly ash and use it in the agricultural industry as soil amendments. So, though it is surprising, it is possible. The study shows that the growth of crops is higher after the soil is amended with fly ash that stored with 5% of CO2 compared to controlled situations. We also simulated the saline reservoir condition using these reaction chambers to analyze the well cement behaviors. Here you can see the mineralogical and microstructural changes in carbonated glass G cement. We could witness different reacted zones with distinct physical characteristics on the microstructural images. These findings have been published in the Journal of Cement and Concrete Composites. We also evaluate the CO2 sequestration into steel slag. It would reduce the demand for commercial CO2 sequestration and significantly reduce the required energy and cost. Here we can see with the increase of water to solid ratio, the ultimate sequestration is significantly enhanced. Potentially, this process can store around 30 kg of CO2 into 1 ton of slag. Please visit our paper published in Measurement Journal. As can be seen from our paper published in Renewable Energy Journal, we utilized these custom-made high-temperature, high-pressure reactors to perform long-term geochemical tests for different reservoir conditions. Here you can see some experimental results targeting CO2 sequestration in geothermal reservoirs. We found that microstructural and mineralogical alterations weaken the mechanical properties of specimen with time. We also identified possible precipitation of clay minerals during the long-term reactions. This emphasizes CO2 sequestration possibility during long-term operation in CO2-based geothermal reservoirs. These findings have resulted in collaborating with colleagues from Europe to use CO2 as stimulation and circulation fluid in geothermal energy extractions. Moving on to my final slide, here are a few highlights from my talk. Over the last 2 decades, tremendous development has occurred in laboratory experimental facilities around the world that can simulate real rock behavior under in-situ stress conditions. Our 3G Deep Earth Energy Laboratory at Monash University in Australia has state-of-the-art research facilities to conduct advanced research on rock characterization and fragmentations. These laboratory facilities are vital to characterize deep rock mass, simulating high in-situ stress, high temperatures, and high pressures. We have also adapted a 4-scaling principle, microscale, mesoscale, and macroscale, to understand and solve reservoir scale problems. In this presentation, I talk about a couple of selected facilities and their applications across macro to micro scale, including our super deep stress reactor for mineral and energy recoveries, large-scale co-flooding equipment, deep geothermal facility, fracking apparatus using foam-based fluids, large-scale direct shear testing facility, X-ray transparent flow cell, an in-situ CT imaging technique, and our high-pressure, high-temperature saturation reactors. I hope these facilities I shared would provide you valuable inputs to strengthen your experimental research, to solve different geomechanics and deep mining problems. We continue to improve our laboratory infrastructures. If you are interested in collaborating with us and supporting our research at 3G Deep Research Group at Monash University, you can reach out to me. I'm eagerly looking for innovative ways, particularly thinking outside of the box solution, to find sustainable solution for resource recovery from the earth and contributing to UN Sustainability Development Goals and to achieve net zero emissions. Thank you very much for listening to my talk.